Hello, my name is Aedan Coulter, and along with Noah Kantor and Fino, we will be exploring how the random decision forest algorithm in Tersett's land change modeler works. A good place to start is with the question, what is a decision forest? A decision forest is a collection of many other algorithms called decision trees that work in conjunction to create a map of transition potentials. A decision tree is an algorithm that takes data and splits it repeatedly until all of the data is split into homogeneous bits. The decision forest then takes the results of all of the trees and averages them together to create a final transition potential map. Here is an example of a decision tree, with labeled definitions of the components. Feel free to pause the video for a few moments to go over any of them. Here is a screenshot of the random decision forest submodel in Tersett. Sample size per class determines how many pixels of change and persistence are given to each tree. 50% of these pixels will be used for training, and 50% of these pixels will be used for testing each tree. Number of variables as split determines how many variables are available at each node to split the data with. Number of trees is the amount of trees in the forest. Decision trees decide when to split based off the Gini index score of each possible split. When given two variables at split, the algorithm will first select 2 of n variables inputted, then calculate the Gini index score of each possible split of the data for both selected variables. In the description, there is a link to a video explaining how Gini index score is calculated. Now for example of one tree. Here we have 20 pixels of persistence and 20 pixels of change inputted into the root node. We are using the predictor variables, distance from built, geology, and elevation, with the number of variables selected at split being 2. Here it needs to decide how to split the data. The program calculates the 20 meters from built parameter as being the best split, and places 14 pixels of persistence and 5 pixels of change over 20 meters from built, and 6 pixels of persistence and 15 pixels of change under 20 meters from built. This is our first split and resulting in 2 decision nodes. We will be following the under 20 meters from built node.
Note that, while we are following this node for the sake of example, splits will continue on the over 20 meters from built side. You can see the entire tree with remaining splits at the end of this section.
From here, the algorithm determines that the parameter elevation of 130 meters best splits the data and places 5 pixels of persistence under 130 meters and 1 pixel of persistence and 15 pixels of change over 130 meters. The under 130 meters node is now a leaf node.
Finally, the algorithm determines that the parameter geology type best splits the remaining data. It splits geology types A and not A, with 1 pixel of persistence in A and 15 pixels of change in not A. Now the tree is constructed, and new data, the full extent, is inputted into the built tree and classified as change or persistence. Then all of the tree's results are averaged together into the decision forest, and a transition potential map is outputted.
Now I will show how changing the number of trees affects the outputs of the model. Here are the outputs of the model when just one tree is used, using distance from built as a predictor variable and the other parameters being set to default. The transition potential map on the left shows which areas are less likely to transition from non-built to built and which are more likely. With just one tree, there are only 2 possible transition potential values, 1 and 0. The histogram in the center shows about 30,000 pixels have a transition potential value of 1, while more than 50,000 have values of 0. Notice the cluster value is at 1 at the top of the regression plot. There should also be a cluster at 0, but that is cut off by faulty plotting in Tersett. When 5 trees are used, the outputs are noticeably different. This time there are 6 different transition potential values rather than just 2, and you can see a gradient of transition potential values in the map. Note the horizontal clusters of transition potential values in the regression plot that match the values in the histogram, except for the bottom 2, which are again cut off by a plotting error in Tersett. The pattern continues as we increase the number of trees to 10, with more possible transition potential values and the map of transition potential values appearing smoother, with an even clearer pattern visible of which areas are more likely to transition. You may be wondering how the transition potential values are calculated, or why there are only a certain number of transition potential values. Let's go back to the example of 5 trees. You can see that there are 6 transition potential values in the case of 5 trees. For each pixel, each of the 5 trees is applied, and each tree will produce a different prediction for the pixel as to whether the pixel will transition from non-built to built. If the pixel is predicted to transition, it will get a value of 1. If not, it will get a value of 0. The way transition potential is calculated is that it is the sum of the values produced by each tree divided by the total number of trees. For example, if 3 out of 5 trees predict that the pixel will transition, the transition potential of that pixel will be 3 out of 5, or 0.6. If no trees predict transition, then the transition potential value will be 0 out of 5, which is of course 0. This means that the possible transition potential values are a direct consequence of the number of trees, with the possible transition potential values being multiples of 1 divided by number of trees. In the case of 5 trees, it means all transition potential values are multiples of 1/5, or 0.2, which matches the values displayed in the histogram and regression plot. You can see where different transition potential values are located on the map, roughly following the pattern seen in the distance from built predictor variable.
Another important parameter to consider when using the decision forest model is the number of variables at split. The variable the model uses to split the data is not chosen from all the variables, only a subset of variables. The size of that subset is determined by the parameter known as number of variables at split. Changing that parameter changes the size of the subset. Okay, so here, number of variables at split is set to 2. This rectangle, which shows the subset, can only hold 2 variables. If I change the size of the subset to 1, then the subset can only hold 1 variable. If I change the size to 3, then it can hold all the variables here. It is important to know that it is random which variables end up in the subset. So if there are 2 variables at split, and then therefore 2 variables in the subset, those variables could be A and C, A and B, or B and C. To test the importance of the number of variables at split, we ran Decision Forest several times. We used 3 variables: elevation, geology, and distance from 1971 built. The default sample size and number of trees were used for all runs. First off, we compared 2 runs, one with 1 variable at split, and the other with 3 variables at split. Look at these maps and histograms. While there are differences such as the different means and how the heights of some bars on the histogram are not the same as the counterparts on the other histogram, they are nearly identical. However, despite how this makes it seem like variables at split doesn't matter, we cannot say that for certain yet because Decision Forest is a stochastic model. To see how much the model's stochasticity influenced the results, we performed 3 identical runs of Decision Forest with 1 variable at split, runs A, B, and C. We then reclassed the transition potentials into quartiles and 0, and then compared each pair of runs to see which pixels increased, decreased, or kept the same quartile between runs. Can you see any difference between these maps? We then repeated this process with one run with 1 variable at split, and another run with 3 variables at split. Notice how this map looks similar to each of the maps on the previous slide. The similarities between all the results allow us to believe the number of variables at split has minimal outcome on a decision forest model. It seems less impactful than the natural stochasticity of the model. However, according to Tersett's documentation, this parameter becomes more important as the overall number of variables increases.
Thank you for watching our video on the decision forest algorithm in the land change modeler. We hope it has been informative and you are now able to better understand using this tool. Thank you.